Hi, everyone. In this tutorial, I would like to share with you how to create a building energy model and simulate it using topologicpy. I recently posted something about this on LinkedIn and Twitter and received a lot of interest from people who are asking how to do this. So my name is Wasim Jabi. I am a professor of computational methods in architecture at the Welsh School of Architecture, Cardiff University. So let me get started with this and show you some of the requirements. Obviously, creating and simulating energy performance is not an easy task. It requires a little bit of work. So you do need to be comfortable with the concepts behind and the science behind energy analysis, as well as Python programming, because topologicpy is now a standalone Python environment, Python-based environment, and it's best run within Jupyter Notebook or another Python editor. So let me tell you what the requirements are. First of all, as of this video, you will need topologicpy version 0.3.9, which has solved a few of the bugs that were in the previous version. And I know I've tested it. I think it runs quite well, but obviously nothing is perfect. If you find any bugs or issues, please submit on GitHub issues or contact me and let me know. Also, this version uses openstudio SDK 3.5.1. So if in the future they come up with a new version, I will try to update topologicpy to use that. openstudio as a Python API is included as a dependency for topologicpy. So if you install topologicpy using pip install topologicpy, and if you have a version already, you need to add -- upgrade, right? As you know, from pip install, make sure that topologicpy is 0.3.9. If that is installed correctly, it will install openstudio for you. But in addition to the openstudio Python library, you need to download the openstudio application, which is the graphical user interface for openstudio. And that you can download from openstudio.net. Then, in order to get started, you will need to download geometry, weather, and template files if you don't have your own. There are some examples on my GitHub. If you go to that website, github.com/wasimj/topologic_tree/main/examples/topologic energy, you will find all the files that you need to get started to do kind of like an example. But hopefully later on, you will have your own geometry, your own weather and template files to get started. Obviously, you need to be familiar with the topologicpy API, and that documentation is available at my website, topologic.app/topologicpy_doc. And this tutorial today will run on Windows 10 using Jupyter Notebook, which is a really nice environment for running Python applications. So I will show you that. So let's go ahead and get started. One thing I forgot to mention and add here is that you also need to identify an output folder for the energy results. So just create, let's say, a folder called energy models on your desktop and specify that in your script, and all the files will be saved there. All right, so let me go ahead and share the whole screen now. And I will type this script from scratch. It's a very long script, so take your time and make sure you don't make any spelling mistakes, because that's 90% of the errors come from really mistyping stuff. So I will share the whole screen, and let's go ahead and this is the script. I just want to show you what it looks like. It's quite extensive, but we're going to type it from the beginning. But at the end, we will get a three-dimensional model with color-coded spaces. So these are 4 spaces on each floor, and with one large atrium or core, if you would like to call it that, at the bottom. And it's kind of a continuous space from the bottom to the top. The big rectangles that you see here on each side are the windows. And the little extensions here are shading surfaces, as you can see here. So this is basically south, and that is north over there. Okay, so let's get started. So I'm going to create a completely new file from the beginning. Great. Now you might see me look down because I have my notes and I will be kind of checking them just to make sure. Now the first two lines that I'm going to type, you do not need to type if you have pip installed topologicpy, but I am on my software development machine and I don't have it installed, so I have to point Jupyter to where topologicpy is installed, and this is done using sys, import sys, and then the next one is to sys.path.append, and then I have to give it the address, the folder name, I mean. So users, for CMJ, documents, GitHub. That's my folder for GitHub. And that's where topologicpy is saved. So I'm just going to run this. And that should be fine. So you will start from this next cell here. So we're going to first import all the topologicpy classes and modules that we need. So in order to see those, let me just make sure this is a bit larger so that you can see it. Okay, hopefully this is large enough. So let's go ahead and look at the documentation. So you'll see this here when you get there. So there's some information on topologicpy, but then you press enter, and we are at 0.3.9, as you can see here. And then this is a really well organized and clear API documentation. So for example, if you want to find out how to make a vertex, you click here and you say, okay, it's by coordinates. So you give it X, Y, Z, and makes a vertex and stuff like that. So, and then you can go back. And then the stuff that's related to this module, to this tutorial, excuse me, are the module's energy model. So these are the energy models, methods, and also Plotly, which will allow you to visualize it on the screen. And of course, topology and other things that will allow you to import a BRAP and do all sorts of things. They're really quite extensive set of classes and methods. Okay, so all right, so let's go ahead and import some of the things that we need. In topologicpy, the classes and the modules have the same name, meaning that there is a file called vertex, and inside that file is a class called vertex as well. So in order to import it correctly, there's a pattern that you will always follow, which is to say from topologicpy, sorry, I'm just typing here, dot vertex, import vertex. Okay. So you will use that. So we're going to import things that we need. So I have them here as a list. So I'm going to just go ahead, type them in from topologicpy.face, import a face, and from topologicpy.cell, import cell, from topologicpy. It's typing a lot today. CellComplex, import CellComplex, from topologicpy.cluster, import cluster, and from topology, import topology, from topologicpy.dictionary, import dictionary, and from topologicpy.color, import color, and from topologicpy.plotly, import plotly, and from topologicpy.energy model, import energy model, which is the main one. Great, let's run this. Okay, that's run correctly. Okay, so the next cell. So now we need to specify the weather files, the design day files, where the OS binary path is, all of these things, and the output folder. So I have several variables that I set for those, and you need to point them to where they are stored on your computer. So on my computer, weather file path, I have something called weather file path. I'll set it in a second, but let me just tell you what they are. Design day path, design day, excuse me, file path. I have something that is called design day, and I have the OS binary. This is where the, and this is called just path. And the output folder. And the building path, that's where the CellComplex is for the building, the actual geometry of the building. And I'll show you what that is in a second. And then the apertures means windows. So these are, again, it's a cluster of apertures that you will apply to your building. And I'll talk about that as well. And then the shading path, the shading set of faces that you saw that are coming out of the building. Okay, so what are these things? The weather file path is the path to the EPW file, okay? The design day file path is a path to the .ddy file. The OS binary path is the path to the openstudio.exe file. The output folder is where you're gonna save your results. The building path is a path to a brep file, to an open cascade brep file, which topologicpy can read. Or you can import from an OBJ file, for example, and transform it. It's completely up to you how you get your geometry. The apertures, again, is another brep file, which is a cluster. And the shading path is a cluster or a set of faces, I believe. I think it's a cluster of faces for shading. So where do we get these things? So let's go ahead, first of all, and get the weather design and find out where those things are. So the way I'm going to do that is I'm going to go to, as I said, this web page, which is on my GitHub. And you'll notice that I have, under topologic Sverchok examples, topologic energy, we have all of these files here. So for example, I use the Gatwick, the London Gatwick files. And I would suggest that you download these 3 files here. So let's go ahead and download them. And basically, I have them downloaded, so I don't have to do that. And then there is a template that you need, which is this office building, for example, template. Let me see if there's a better one. No, I think that's it. And then there are the topologic building BREPs, like this BREP. And then the shading surfaces BREP, and the topologic apertures BREP right here. So I have those already downloaded, and I have them on my GitHub. Excuse me. Let's go ahead and see where those are. GitHub, topologic Sverchok, and examples, and topologic energy. So I have them already here. So let me just show you what they look like. So for example, the topologic building BREP. Looks like this. Okay, so if we do like a mesh edges or a hollow mesh, so it's just a building. And the shading surfaces are just these shading surfaces, and the apertures are the windows. Okay, great. So let's get back to our work here. Sorry, let's go ahead and close these. All right. So we are back here. So I'm going, instead of like typing all of these things, because yours are going to be different, I'm just going to go ahead and copy and paste them from the pre-made file. So I'm going to go over here, and you can see them all set up here. I'm going to go ahead and bring them over. Great. Okay, and I specified also an output folder which is on my desktop called energy models. So let me show you that. So I go to energy models here, and you'll notice that in energy models, there is a timestamp. Every folder has a timestamp so that if you keep running the building simulations one after the other, they will not overwrite each other. Every time you run a building simulation, it will create a new folder and it will timestamp it, as you can see here. Inside here, you have the standard Energy Plus outputs, and you can get, for example, the web page that shows you all the results. Okay, so that's that. So let's go back here. So we have all of these in here. So let's go ahead and run this. Okay, so now after this, we need to get the apertures and apply them. All right, so let's go ahead to do that. I think I'm gonna do something else. So let's go ahead and get the shading surfaces first. So the shading surfaces are topology by imported brep, and brep is spelled in a strange way a little bit, so you gotta be careful with it. It's B, uppercase R, and the EP are lowercase, and then it is the shading path. The shading path like this. So this method by imported brep goes out, finds a brep file, which is the path, brings it in and makes it into a topology. So those are the shading surfaces. Okay, now the building itself is a same thing, topology by, let me just see if I can spell, no, I cannot spell, okay, by imported brep, and it's the building path. Great, that's the building. So now what I'm going to do is I'm going to decompose this building. The reason I want to decompose it is because I want to get the bottom floor, the bottom face, excuse me, of each cell in order to color code it. So I don't want to color code the whole cell. I just want to color code the bottom faces, and I want to use that for the visualization. So how do I do this? I'm going to create a CellComplex.decompose method, or not, I'm going to use it, I mean, and create a dictionary. So CellComplex.decompose building returns a dictionary, and that has keys in it. And in those keys, there are things like external faces, internal faces, internal horizontal faces, bottom faces, top faces. Everything is decomposed out of a building that is a cell complex. You get every set of faces as a cluster saved in a separate dictionary entry. And that is really useful to do that. If you'd like to know more about CellComplex.decompose, you need to go to topologicpy here, the documentation, go to CellComplex, take a look at decompose, and you'll notice that it gives you back a dictionary, and it has these keys like top horizontal faces, internal vertical apertures, external inclined apertures, whatever it is, it will all be listed here. All right, so out of this, so what are we gonna do with this? We're gonna get the external faces. So the external faces is equal to D, and it is external vertical faces. Okay, external vertical faces. Great. Now, why am I getting the external vertical faces? I'm getting them because I need to shrink them and make a window out of them. Okay, and there is a shorter way to do it in energy models, which you can just simply specify a window to wall ratio, and it will apply it for you. But I'm doing it kind of the long-winded way, which is to actually create a design for the apertures, which is by shrinking the external walls and making a face. And I will give it a scale factor. So I'm going to make an empty list for apertures, which I will fill with these new apertures, the new windows that I'm going to be creating. And I'm specifying a scale factor of 0.5 for now. And I'm going to go ahead and start shrinking every face and creating an aperture. So I'm going to do a loop. So for F in external faces, I'm going to get the centroid of the face, topology.centroid, because that is the origin by which I'm going to shrink. It's the origin of the scaling. So I'm going to shrink along that centroid. So that's the centroid, C. And then for apertures, I'm going to append a scaled version of that face. So how do you scale? I'm going to say topology.scale F, and the origin is C, and the scale factor on the 3 X, Y, and Z scale factors are all the same, is SF, which is 0.5. Okay, so this one line gives me all the all the apertures done in one go. Great. So now I need to add these apertures to the building. So the new building is going to be equal to topology.add apertures. And I'm going to add it to the building that I got by imported brep. The apertures is the list of windows, and exclusive is true. Take a look at that API to understand what that means. But basically, every window is applied only to one wall. Once the wall gets a window, it doesn't go anywhere else. So it's just a quicker way to do it. And I want to apply it to subtopology type face. And that's it, really. The tolerance can stay the same. Okay, so basically I'm saying take these apertures and apply them to the faces of the building. That's what this method does. And return the whole result into a building. The building now will be a cell complex with apertures built into it, which the energy model can recognize. Great. So now it's time to create an energy model. And so we say model. This is a model means energy model in this case is energy model dot by topology. And what are we giving it? Where the building is equal to the building. The shading surfaces are called shading surfaces as well, same name. And the glazing ratio for anything, this is, you don't need really, is equal to SF. This is just a precaution. You really don't need it because you already have apertures added to the building. But if you did not have apertures, you would simply use the scaling factor to add a glazing ratio. Again, energy model by topology, we can go here, go back here to energy model, look at by topology, and you can read about all of these things. Okay. Right now, so why did I not specify weather file path, design day file path, floor levels, building name, et cetera, et cetera, et cetera? All of these have defaults, and if you do not specify them, they topologicpy has built-in weather files and design day files, so you can actually load those in there. But if you want to use your own, you need to specify them. The OS model path, for example, is a path to a template OSM file. The default is in there in assets, energy model OSM template office building 3.5.0. So this OSM file is a file that has default constructions, you know, all kind of the materials, everything is specified in there. But it doesn't have any geometry. It's just ready to be populated with geometry, and the geometry comes from topologicpy. Okay, things like also where is the north axis, the cooling temperature, which is set to 25, heating temperature. This is wrong. This should be 20, not 25. So I will fix the documentation. And everything. You can even specify custom space names and custom space types. So not everything needs to be an office. Again, you can choose different space types from the template that's provided. Great. So I'm going to go ahead right now and just simply print the model so that you can see what it is and run this just to make sure it's all working. Here we go. So this is the actual model. So it's an OSM file, basically, in other name. So that is the model. And if you look at the class of the model, it is an openstudio model core.model. Okay, so that is created correctly. Great. So now that we have a model, let's run it one more time just to make sure. Now we can run a simulation. Right. So we can say model is equal to energy model oops, dot run. That means run a simulation. We give it the model. We give it the weather file path, which is weather file path. And we give it the OS binary path. So we did need all of these, OS binary path. And we give it the output folder, which is equal to the output folder. And all of these obviously are coming from here. Okay, so this is going to take a little bit of time, not too much, but it will. And it will tell you it's running the simulation. The progress bar, yeah, there is a progress bar, but it kind of like jumps to 100% immediately. But at least it gives you an indication that it's running. We just wait for it, and we wait for this asterisk here to turn into a number. Okay, so now the model has been run, and you should see a result in your output folder under energy models. We can do by date. Here's the energy models. And you can see there's now a new folder. Great. So what's the next step? So now that we have the model, we can start getting information out of them. So first of all, we can get back the topologies out of the model. Now, why am I have the topologies, I already have a building. Why am I getting them back out of the model? The reason I'm getting them out of the model is because now they have dictionaries with assigned space names and space types, and everything is consistent. So I can get the dictionaries out of those and use them for the SQL query to get the values of the simulation. So I'm going to get topologies equals energy model.topologies model. And then I'm going to get the cells out of those topologies. So topologies is again, it's a dictionary. So let me go ahead and print it for you so that you can see what is inside topologies. So let's go ahead and run this. Okay, so it's a dictionary that has cells, has apertures, has shading faces, etc. So we are getting the cells out of them. And then we have a list of values that we're going to get. So I'm going to initialize it with a empty list and groups. I'm not sure I'm going to use groups, but let's go ahead and do an empty list called groups. Okay. So now, just for the example for this tutorial, excuse me, I'm going to get 3 visualizations. I'm going to get the zone sensible cooling, the zone sensible heating, and the time not comfortable based on simple ASHRAE 55-2004. So those are 3 tables and 3 results that I'm going to get. So I'm going to get the first thing I'm going to get is the, let me just check really quickly. The report names, I believe. I'm missing that somewhere. So let's go ahead and get those from here. So you notice here I have reports, 4 strings, table names, column names, and units list. So you need to read them kind of like vertically this way. So the first one is, the report is called HVAC sizing summary. It's for the entire facility, and I'm getting the table name called zone sensible cooling. And from that table, I'm getting the column called user design load. You can get calculated loads or something else. And you need the units for it. The units is in watts. So that is one result. Sizing summary, entire facility, sensible cooling, user design load, and watts. The next one is also sizing summary, also for entire facility, but it's zone sensible heating, and it's also user design load, and it's also in watts. The third thing I'm getting is system summary and for the entire facility. And as I said, time not comfortable for summer or winter clothes. And that is, the units of that is our HR. So I'm going to get these and copy them over just to speed things up a little bit and put them here. And the nice thing about this is that then I can say, just give me the index. Just index 0, it will give me index 0 for reports, for 4 strings, table names, column names, and unit list, and it will just simply give me everything in one go. So how do we do this? As you can see here, I say index, and then I get all of those units. So I'm going to copy that as well, because these are simple things. So you'll notice here, I'll start with 0. So basically, when I say index 0, and I get the report name, reports for string, table name, column name, and units, it will look into these lists and gets the first element of each, and that will be my report. And if I later on change it, I just need to change index, and it will get the rest of it. Now, how do we get those names? You need to know the openstudio API, and also if you look at the HTML file that was created, it gives you a hint. The names are not always the same, like system summary would have a space in between, but you can get those things. And I have a API for them. So you can get, for example, the report names, all of them, and you can choose automatically, or at least you can read them. You can get column names, table names, row names, etc. All of these are available. So you don't have to guess if you would like, just print them out and choose the one that you want from there. Great. So units, we are at units. Great. So now we need to get a value and save it. So we're going to go through the cells one by one and find out what is the value that's associated with that cell. So for cell in cells, we're going to do a loop. We're going to get the dictionary of that cell, topology.dictionary cell. And we're going to get the name of that cell. So dictionary value at key. We give it the dictionary, and the key is called topologic underscore name. Topologic in uppercase, underscore name is in lowercase. So I know that topologic creates these names. So this is the name. In the SQL file, the name is appended with underscore thermal underscore zone. So we need to change the name a little bit. So name is equal to name dot uppercase, so upper, because it's all in uppercase, plus underscore thermal underscore zone. So let's go ahead and print the name for now, just so that you can see that. And let me run this one more time. And am I printing something else? It looks like. Okay. Oh, dictionary is misspelled. Where is it? Here. Dictionary. Yeah, let me not print the topologies here so that you can see them. And yeah, it's corrected dictionary. Print it one more time. Okay. So this is now the correct kind of way it's named. And if you notice in, where is it? In the topologic building here, you'll notice that these are the same names here. So that's where we are getting those files. Okay, great. So we can take out this print name now. So now we need to get the value. So the value is equal to energy model dot query. And we're going to give it the model. We're going to give it the report name. So the report name is equal to report name. We're going to give it the report for string. This is the one that's called entire facility. Report for string. And table name equals table name. Column name equals column name. And row names. So this one actually, this method query takes a list of rows names and gives you back a list. So since we are doing it one by one, we need to place name inside a list made out of one item. So you put it in square bracket, that's the name that we're using. And units is units. And because it's going to return also a list, we could simply put 0 here in order to get the first element. I could have done it in a different way, which is to create a list of names and then just give it all at once, and I get a list of values. You could do that as well. Okay. Okay, so let's go ahead. Before we exit from here, we can say values is equal, or values dot append, excuse me, value. So basically, we are, and do we have values? Yeah, we have values here. So we're appending this value to the list of values. Great. Right, so next, we need now to start visualizing. So let's go ahead and print those values so that you can see it. Okay, so these are the values, and this is for index 0, which is zone sensible cooling. So let's go ahead and change the index and shift print again, or shift run again, excuse me. And these are different values here. And if we do 2, great. So let's go ahead, go back to 0 or cooling. So I'm going to go ahead and remove this print and run this one more time. Great. So now what's left is to visualize it in Plotly. So we're going to do 2 steps. We're going to draw the building as a translucent envelope, and then we're going to draw the faces with the color coding. And it looks nice when you have them both together, rather than just faces floating in midair. You put the whole building, but you draw it in translucent so that you can see through it. If you want it to be completely transparent, you can just draw the edges and the vertices, but not the faces. And you can just see, get a wireframe, and you can see just the faces, the floor faces, with the color kind of undistorted by any kind of shading. So I'm going to make a cluster, which is a cluster by faces, or cluster by topologies, excuse me, faces. So you'll notice that, oh no, sorry, I missed a piece here. Sorry, first, not here, I'm kind of like skipping ahead. So let's go ahead and create data first. So data is going to be the plotly data that will be plotted onto the screen. Okay, so it's a list, and I'm going to start with an empty list. So now I'm going to get a cluster of the building. So cluster by topologies, cells plus apertures plus topology.faces, shading surfaces, because that's a cluster. So I'm taking the cells, the apertures, the faces of the shading surfaces. I'm making a big kind of like list out of it, and creating a cluster. So now if you want to see this one, you can just simply say topology.show cluster. And let's go ahead and, sorry, faces, yeah, not faces, there's a D here. Great. So this is what I'm drawing here. And this has a default face opacity of 0.5. Okay, so I'm not going to use it this way. I am going to create a data out of it. So data, which is here, plus equals actually to plotly data by topology cluster. And I'm going to set the face opacity to 0.1. Okay, so now if I want to say, I'm not going to draw it right now because you can make it, you need to make a figure out of it and then draw it. Topology.show is a shortcut to all of this. But if you want a lot of control over the look of it, you need to go through the steps of creating plotly data, a plotly figure, and then show the figure. So okay, so now so we have the overall envelope. Now we need to do the color coding of the faces. So what I'm going to do is go through the cells and then get their bottom faces and assign the values to them. So for I, cell in enumerate cells, which gives me the index as well as the object. If you look up enumerate, if you don't know what that does, we're going to get a dictionary when we decompose. So we're going to decompose the cell, and we are going to get the bottom faces. So the bottom faces are equal to D, the dictionary, and it's called bottom horizontal faces. For every cell, I'm going to get the horizontal faces. And then for bottom face, because there might be more than one, in most cases it's just one face, but a cell could have multiple bottom faces. So for bottom face and bottom faces, we are going to apply this. So in order, I'm going to find the value of it, but we need two things. We need an empty list of faces, and we need an empty list of selectors. And I will tell you about that a little bit later. Okay, so we are going to get a dictionary. So dictionary by keys values, or I'm going to create a dictionary. And the first key is value. And the second key is a label. This will be used for drawing later on. And the actual values, these are the keys, value and label. are the keys. And the actual value is values I and string round, and I'll explain all of this in a second. I2. So what am I doing here? So let me go ahead and close all of this. So basically, I'm creating a dictionary and I'm giving it two keys. One key is the actual numeric value that, which is like the cooling load or the heating load. And I'm also giving it a label in order, if you hover over it, you can like maybe see the label, which is a string. It's an actual text of the same values. So sorry, I made a mistake here. Values sub I, and then I'm rounding that only to 2 decimal points. So that's another long label. And I'm applying it to a key called label. So I'm creating this kind of dictionary here. Great. So now I'm going to take this bottom face and add it to the list of faces. So faces.append bottom face. And S is equal to face.internal vertex. I'm getting an internal vertex from the bottom face. And I'm setting the dictionary to the selector. Topology.set dictionary. I'll tell you exactly what that is in a second as well. Unfortunately, you have to type it in, and then I have to explain it, and then selectors.append S. So what is this business with selectors? What are we doing with selectors? Selectors are vertices, are three-dimensional vertices, and they are placed somewhere in space, usually on faces or inside cells, and they help topologic associate a dictionary with an element like a face or a cell. And so a selector is basically an identifier of the face. As long as it's sitting on a face or inside a cell, topologic will know that whatever dictionary is inside that selector should belong to the enclosing entity. Okay, so there is a method that takes a topology, takes a list of selectors, and automatically transfers the dictionaries from the selectors to the appropriate sub-entity in that topology. And that's why we need these selectors. So basically, I am looking at the value inside the cell, and I am applying it to the bottom faces. Okay, great. So now, I'm going to make, so I'm going to get out of this list. I have out of these two lists, and I'm going to make a cluster by the faces, cluster by topologies faces, and I will now transfer the dictionary. So the cluster now is equal to topology.transfer dictionaries by selectors, excuse me, transfer dictionaries by selectors, and I will give it the cluster, I will give it the selectors, and I will tell it to transfer faces equals true. So only transfer to the faces. And that now we have the cluster with the faces and they have the right dictionaries. So we're going to specify the color scale. This is a Plotly color scale, like we read this, and thermal and spectral and all of these things. You can find a list of them. I'm using the thermal because that seems appropriate for thermal analysis or energy analysis. And then I'm going to create now a new Plotly data for the faces, for the color coding. So data, the original data list, as you can see from here, I'm going to add to it. So plus equal means I'm adding to that list. And I'm saying Plotly data by topology, by topology. And it will require the cluster. Face opacity is full opacity. So I'm going to say face opacity is equal to 1. Face group key is equal to value. So this is the key that it will use in order to define the color coding of the face. Face label key is equal to label. If you notice, these are the same as ones we used here. And the face groups, in order to figure out the color, is called values. Okay, so it will find the value key, or the value of the value key, and it will look it up in the list, and that's how it will determine the color based on the color scale. So values. What else do we have? Let me just check from the original, because I'm missing it here in the print. Let's go ahead over here. Data. Okay, face and the color scale, we need to give it the color scale. That's not the only thing that's missing. So basically, color scale is equal to, is it color scale uppercase S or lowercase s? Uppercase S, and Mantissa is 2. Okay, so color scale is equal to color scale and Mantissa. If you look up Mantissa, Mantissa is the number of decimals after the number of places after the decimal point. So just to kind of not have like long numbers on the color bar. So this is the data, and then we need to create a figure by this data, if I'm not mistaken. So let me just check here. Yeah. So this is the line for it. So figure is equal to plotly.figure by data. We give it the data, and we give it the width and the height in pixels. And then we can also add a color bar to this data. So figure is equal to plotly dot add color bar. We give it the figure to add it to. The values is equal to the values that we have collected. The width of the color bar is equal to 30. We're just customizing them. The outline width is equal to 1. The number of ticks and ticks is equal to the length of the values. All of these you can omit and just simply say plotly add color bar figure values, and it will just simply use the defaults for this. The title is the table name, and the subtitle is equal to the column name, and the units is the units. The color scale is the same color scale that we're using, which is thermal, and Mantissa is equal to 2, which is 2 decimal points. And then we say plotly.show figure. So let's go ahead and see that figure. Oh, internal vertex is not defined. Oh, I have a mistake here, a typo. This should be face dot, oops, internal vertex. Oh, some more stuff. Oh, color scale, sorry. Again, another typo. Where is that? Color scale here, color scale, color scale. Oh my gosh, Mantissa. Okay, data by topology. It does not like Mantissa. Okay, so maybe it's not available here. Okay, so we'll take it out of here. Color bar is uppercase. We'll get there. It's just a lot of typos. Here we go. So this is zone sensible cooling, and these are the values. So let's go ahead and exercise this. So we can go back to here, to this cell, and say we would like to get the zone sensible heating. So we'll change this to 1, run this one. And then once it finishes, see, once you see it here. Okay, so now we can run the other one. So here we go. This is now zone sensible heating. And let's do one more. Now we're gonna get the time not comfortable in hours. Run this one more time. I mean, the nice thing about it is that you're not running the whole simulation again. You're just running the SQL query. So it's a lot faster. I'm just waiting for it to finish. Yeah, it did finish. So let's go ahead and run it one more time. And this is the number of hours where it is not comfortable. All right, that's it. Thank you.